Well, alphabetical order, last but not least, we have Charlie Westbrook, class of =67. Charlie is one of the pioneers in combustion modeling and has been highly recognized. The Thomson Reuters named him one of the world's most influential scientific minds. So, Charlie.
Having lived my whole life as a W, I'm used to being the last in line. And in another way, I'm sort of like a dinosaur. I'm not going to go with slides. I'm just going to sort of talk for a few minutes and then let everybody go to lunch. I graduated in 1967, and it was right at the takeoff time for the whole computing world. The computers we had on campus while I was an undergraduate were really, really primitive. There were a couple of lunatic engineering majors who'd spend all their time in the computer lab playing with it. They're the ones who ended up making a lot of money in their careers. But mostly it was just an oddity at the time. The only useful computing thing that I ever learned as an undergraduate was how to run the key punch thing for punching IBM cards, which turned out to be very useful because that's all they used at the place where I went to work. And so all of a sudden I was at least able to get started. My next door neighbor at work, this is all at Lawrence Livermore, I was awarded a Fannie and John Hertz Foundation fellowship, which in those days was the most lucrative graduate fellowship available. I interviewed with Edward Teller, who was the head of that foundation, and he asked me questions I still don't know the answer to, but somehow I got selected for one of these fellowships. And what he was trying to do was he was trying to jumpstart the discipline of computational science, using computers to solve practical problems. And so that's really what I spent my whole career doing. I started as a physicist at Lawrence Livermore, doing some classified work. I did a thesis in computational astrophysics. In those days, you noticed that a lot of astrophysics research was coming out of the weapons labs because they had the same physics as the stars and the bombs. And that was a way for all these bright physicists to get a publication career, is to just change the length scales and the time scales to what they were doing under classified conditions and publishing them in the astrophysics literature, and that's what I did for my thesis. But when I finished my thesis, there were no jobs in astrophysics, and so the guy who was had an office next door to mine was one of the pioneers of climate modeling, atmospheric chemistry. And he said, atmospheric chemistry is the next important thing in the world. By the way, there's another discipline starting up right now, and that's combustion chemistry. And that's just the same as climate chemistry, so why don't you try that? It took me five or 6 years to realize he was wrong, but by that time I was already committed. So I've spent my whole career, really, working on solving puzzle problems. I'm a great puzzler, and so I like to pose interesting problems as puzzles. And I just want to give you a real quick example of one of these things and then let you go. And that's the problem of solving. I was responsible for solving the mystery of engine knock. And older people here drove cars in the old days that it would knock. Not nice. So I'll tell you the origin of the engine knock problem and how then I went to solve it. And it'll just take a few minutes and it won't keep you here too long. World War I, the first war really that was mechanized, and one of the pieces of that were these airplanes that people would fly over and try to see where the other guys were, and they would have their guys fly over and see where your guys were, and they would engage in these dogfights. And does everybody here have a history of reading Charlie Brown and Snoopy? Everybody knows that. And you remember the dog fights with the Red Baron? Everybody knows that too. Those dog fights really happened in real life. That's why they're funny in a cartoon. But they really happened, and in those dog fights, the guy who had the inferior engine performance died in the dogfight. Instant natural selection. And so people would fool around with their engines to try to get better performance, and what you had to do to get better performance in one of those old gasoline engines was to increase the compression ratio. And the limit to how much you could get more efficiency out of by increasing the compression ratio, the limit was the engine would start to knock. And so if your engine was better than the other guy's engine and you didn't start to knock yet, you would win that battle. But if your engine started to knock, you were dead. So at the end of the war, there was a justifiable interest in trying to figure out what was the source of engine knock. And everybody in the military world and then in the commercial world, because this was also coming up in automobile engines, and that's right when Henry Ford and all these companies started making gasoline-powered automobiles in this country, everybody tried to figure out what was going on with engine knock. And to cut the story very short, and it's fascinating, it turns out that people started looking at additives to fuels, and that's when tetraethyl lead was discovered. Tetraethyl lead, there were better things than tetraethyl lead at being anti-knock additives, but they smelled awful, and the secretaries wouldn't work with the scientists who were using those additives. And so they went back to tetraethyl lead, which was very effective, and we used it for a very long time before people started to understand its problems. Well, starting in about the middle 80s, I started to look at that puzzle problem and trying to understand what the chemistry of engine knock really was and why things like tetraethyl lead were effective at inhibiting it. So it took about 6 or 8 years. It's a classic problem that its solution, it started in the 1917-18 time scale, and here I was in the 1980s trying to work on this problem, and it hadn't been solved yet. Everybody knew which different fuels caused knocking. There were test engines that you could give it a number, an octane number of that particular fuel, but nobody knew what the chemistry was. Nobody understood what the problem was. So, that's, in the first place, that's awkward. And in the second case, it limits what you can do in a research kind of environment to try to improve on the engine performance, which is the bottom line on these things. And so it turns out that you have to write, and this is right out of Moore's PChem, for those of you who were in my era. There were pages somewhere in Moore's book that we used with J. Arthur Campbell, and they showed chemical kinetic equations. And oddly, I must have been perverted. That was one of the parts of that book that I really enjoyed. And I came back to that. Turns out the trick is to write chemical rate equations for all of the chemical reactions that can happen when gasoline burns. And there's lots and lots of things in gasoline that have all sorts of different rates. And a typical calculational problem for a typical gasoline type fuel and solving all the chemical reactions that could happen is there may be 10,000 chemical species in a liter of gasoline or diesel fuel, and about 20 times the number of species are the number of reactions that can happen. So you're solving a stiff set of differential equations, coupled differential equations, with about 20,000 equations. And you have to do it at every time step of the problem and integrate it until it starts to knock or ignite or whatever it was and correlate that. And so it wasn't until the advent of high-performance computing that we could even do a problem like that, which is why nobody in 1930 or 1940 or 1950 was able to solve this problem. Perfect example of the confluence of the development of the tool and final solution of what the problem was. And it turns out that there is a regime as a fuel, as a hydrocarbon fuel in an engine is being compressed by the piston and by the by the burning flame. The last part of the fuel that hasn't yet burned is getting heated rapidly by this compression, and if that ignites spontaneously before the flame gets there, that's knocking. That stuff will explode and create a knock or a ping. If the flame gets there in time, it'll burn it normally, and that's good. And so it's really just kind of calculating the rate of ignition of this end gas, they call it, and comparing it with the time of arrival of the flame. I'm old enough that I remember watching all these cowboy westerns and cowboys and Indians, and when the soldiers would get to save the people in the fort, I visualized this thing as a race. You're racing the flame to burn up that gas. And so that's what we were able to solve. And it's a very, and I didn't want to even show the slides because it would create bad dreams. The complexity of the chemistry in this funny temperature range, it's a funny temperature range between about 600 and 850 degrees Kelvin, and that's all. It turns on at about 650 degrees Kelvin. The chemistry happens, releases a little bit of energy, and then the increasing temperature shuts down that reaction pathway, but it's already done its dirt over that 100 or 200 degrees of temperature, and it has released enough extra energy that it makes those fuels that have this kind of low temperature chemistry ignite. And identifying how to correlate fuel molecular structure, the structure of the molecules that are burning, with what kind of low temperature reactivity they have, and then with octane number, and then when you do it with a bunch of mixtures and like that, that was solving the problem of engine knock. And I've milked that story, including the Snoopy part of it, for the last 20 or 30 years. And that's been the source of all of these awards that I've gotten. And so it's kind of a funny story. The funniest part of it, I'll just leave you with this, is the last walking away message, is I received a medal from the German Physical Chemistry Society. And it was named for a famous professor. And my obligation was to go to Germany and give a lecture in each of the universities that this professor had worked. Unfortunately, he could not hold a job. It took me a month to visit all of the universities in Germany where he had been a professor. And this is the story I was telling to these people at these universities. I had probably given this talk 10 times at different universities until I realized that to them, Snoopy was the bad guy. Thank you for your patience.